So we continue to the next example. We're to use n equals 6 and p equals 0.8 to complete parts A through D below. First, in part A, we are required to construct a binomial probability distribution with the given parameters n equals 6 and p equals 0.8. We have the given possible values of x, and we would like to write out the respective probabilities. We did this earlier, but for the sake of emphasis, we go back to StatCrunch, and I'm going to key in the parameters. In this case, is 6, and we have 0.8 in this case. It has just been coincidental that most of the examples we've considered has p equals 0.80. So going back to our notes, I'm keying in these values, and if I want the respective probabilities there, I can go back to standard, and I'm going to set this equal to individual values, equal to 0. I can compute. I have that value. I can take it back here. And if you recall, we did this computation earlier. Here are those probabilities here. So I'm going to copy all of these values and paste them here. So I have computed all the probabilities there. So the probability of x equals 0 is the first value of 0.000064. And now I continue to the second question, where we are to compute the mean and standard deviation of this binomial random variable using the given formula. Well, the mean will be n times p, and that is n is 6, p is 0.8, so 6 times 0.8, and that will be 4.8. And then the standard deviation is the square root of n times p times 1 minus p. N times p earlier, we got it to be 4.8, and 1 minus p. P is 0.8, so 1 minus 0.8 gives 0.2. And if we multiply that, we get 0.96, and the square root of 0.96 is approximately 0.97998 in this case. Then we are to compute the mean and the standard deviation of this random variable using the table values. Well, if you do this all the way, you will find out that you will get exactly the same mean and the same standard deviation. So without any further ado, this is going to be 4.8 still, and the standard deviation of x is still going to be 0.9798. Then at the end of the day, we also want to graph or draw a graph of the probability distribution of this random variable and comment on its shape. And we are going to find which of this graph below shows the probability distribution. So let's go back to StatCrunch. And here we are in StatCrunch. We have the parameters here, 6 and 0.8. And we can see that this appears to have a longer tail to the left and the hump is to the right. So which of the options given looks like that? Definitely not the first one. Definitely not the last one. Let's see, in this case, it's going to be between this guy and this guy. Which one do you think it is? Looking back, you can see that this goes up a little bit, then peaks, then drops. So let's see. In this case, this goes up a little bit, peaks, and then drops. It is definitely this second one. And in this case, we can say that the binomial probability distribution shape-wise is left skewed. It's left skewed and unimodal. Unimodal, as you recall, from chapter 2 or 3, means it has one mode. That is one mode or peak. With that question completed, we proceed to the next example. In this example, we're told that 13 jurors are randomly selected from a population of 3 million residents. Of these 3 million residents, it is known that 42% are of minority race. However, of the 13 jurors selected, 2 are minorities. Question A. What proportion of the jury described is from the minority race? Given the information that we have, we are told that out of 13 jurors, and how would I write that? Out of 13, 2 are minorities. So this will be 2. And so what is 2 divided by 13? That will be equal to 0.1538. And so I can say that if I round this off to 2 decimal places, that will be 0.15. That is the proportion of the juror that are from a minority race. Question B. If 13 jurors are randomly selected from a population where 42% are minorities, what is the probability that 2 or fewer jurors will be minorities? To answer this question, here are a couple of notes. First, how many jurors were randomly selected? That will be our sample size. What is the probability that from the population you select a minority? That is 0.42 or 42%. And we want the probability now that the number that are jurors from minorities are either 2, that is, it can be equal to 2, or fewer than 2, that is, lesser than 2. So with that said, let's go back to StatCrunch and let it help us with this. So we're going to set the parameters 13 and 0.42. So we have 13 and 0.42, and we want the probability of less than or equal to 2. Compute. You have 0.0431. That is the probability there. So 0.0431. Based on these findings, question C, what might the lawyer of a defendant from this minority race argue? To begin to comprehend this argument that we're going to explain, you should first note that in the entire population of 3 million, you have 42% minority race. Well, as it stands, the probability that you have 2 or fewer here, this is 0.0431. So, given that the composition of the population from which we chose the sample says that you have 42% out of 3 million are minorities, we compared this population or this proportion of minorities on the jury, which does not seem to come close to this. So the lawyer in this case, for a defendant, might argue that the number of minorities on the jury is unusually low, given the composition of the population from which it came. Let's write that down. So we have written that statement down. We now proceed to the next example. According to an almanac, 80% of adult smokers started smoking before turning 18 years old. So we are to compute the mean and standard deviation of the random variable x that represents the number of smokers who started smoking before 18 in 300 trials of the probability experiment. So, as it stands, our x, the number of smokers who started smoking before 11, would be a binomial experiment where the number of trials is fixed at 300 and the probability that an adult smoker started smoking before turning 18 is 0.8. So, to compute the mean and standard deviation, we deploy the formulas for computing the mean of a binomial random variable, which is NP. That will be 300 multiplied by 0.8, which gives 240. Then the standard deviation is equal to sigma and that is equal to the square root of NP times 1 minus P. This is same as the square root of NP is 240 multiplied by 1 minus P. P is 0.8. 1 minus 0.8 is 0.2. And if you multiply 240 by 0.8, 0.2, you have 48. The square root of 48 is approximately 6.9282. So at this point, we ask, what is the correct interpretation of the mean in this scenario? The correct interpretation is that it is expected that in a random sample of 300 adult smokers, 240 will have started smoking before turning 18. Question C. Would it be unusual to observe 270 smokers who started smoking before turning 18 years old in a random sample of 300 adult smokers? These are the steps to follow here. The first step is to compute mu minus 2 sigma and mu plus 2 sigma. That is the mean. The mean was 240 minus 2 times the standard deviation, 6.9282, and the mean again, 240 plus 2 times 6.9282. These two values we are going to get from these two computations would be the fence for capturing what are inliers, that is, non-outliers. Any numbers that fall within these two values will be classified as not unusual, whereas any values below the lower value and above the upper value would indicate an unusual event. So let's calculate these values. The lower value is about 226.1436, and the upper value here is 253.8564. So here's the question. This 270, does it fall in the not usual, that is, between these two values? No. However, it is greater than mean plus 2 standard deviations. And because that is so, we can say that yes, to observe 270 smokers who started smoking before turning 18 years in a random sample of 300 adult smokers would be an unusual event because 270 is greater than mean plus 2 sigma. So the summary of all of that is that to observe 270 smokers in a random sample of 300 adult smokers who started smoking before turning 18 is unusual because 270 is greater than mean plus 2 sigma.